Thank you. Can you see on the right? Can you see yourself? Or okay, that's good. Okay, so today I'm going to, in this short talk, I'm going to talk about this quantum gravity model. It's a paper that I wrote with Markus Reitz and Achim Kempf, and it was recently published. So I think in this series of talks, Achim already talked about the conceptual background of our model. So because my talk is going to be short, I'm going to jump in straight into technical details. So let's start. So the idea is to build a quantum gravity path integral, and the first point in building this path integral, well, we started with this unusual formula, which we call Hawking and Gilkey formula. You can find it in one of Hawking's papers where he cites Gilkey. So this formula, imagine there's a manifold, and then there's a Laplacian operator acting on that manifold. This formula relates the number of eigenvalues of the Laplacian below some UV cutoff to a gravitational action, which is the right-hand side of the equation. So we have an equality between the number of eigenvalues and some gravitational action. And this gravitational action looks like Einstein-Hilbert action with higher order corrections. And so we can use this formula to formulate the gravity action in a different way than usual. So we will, using the right constant of proportionality, we will say that the gravitational action is equal to mu, which is this constant, times n, where n is the number of eigenvalues of the Laplacian. And that's the representation of the gravity action in the eigenbasis of the wave operator. Alternatively, we can also write the action basis independently as, again, mu, and then mu multiplies the trace of the identity operator. So we are interested in having basis independent way of writing actions for gravity and later also for matter, because we want to go beyond space-time representation, and we will sum over all kinds of contributions to the path integral. I'll talk about that later. And just one remark is, please notice for later reference that the ratio between the number of eigenvalues and the volume is some constant plus higher order corrections, and that's going to be important later for a consistency check. Okay, so in addition to a gravity action being represented in this odd way where we say that it's proportional to the number of eigenvalues of the Laplacian operator, we are going to also add free bosons to the path integral. And so the way we write down the boson actions, you can imagine first writing it down as the Klein-Gordon action, but then rewriting it as it's written here in a basis independent way. So this is so we have a sum over the number of boson species, and then trace over the Laplacian operator plus a mass term and the state operator. So imagine that you perform the trace in the position eigenbasis, and then you'll get the usual Klein-Gordon action. Okay, and because we've written it down now in a basis independent way, down there you see that we can also write it in a preferred eigenbasis of ours, and that's the eigenbasis of the Laplacian. So then the action becomes represented as the eigenvalues, the lambda n's, the eigenvalues of the Laplacian, and phi n's, the components of its eigenvectors. And similarly, we also add free fermions to the model. and we basically add free fermions as the square root of the free boson. So the eigenvalues of the Dirac operators are the square root of the eigenvalues of the Klein-Gordon operator, and then we have the Grassmann numbers here. Okay, and so in the beginning we assumed that all the masses of all the species are the same, but then we'll talk about also when we have non-trivial spectrum. So we take all of these actions that are just introduced, the gravitational action, boson action, and fermion. We put them all together and we put them inside the path integral. So that's this e to the minus beta s term in the path integral. To the right of that, I don't know if you can see my cursor, but there are some normalizations that you can ask me about. It's not so important. Sorry. Oh, you can see it. Okay, good. And then what we do in this path integral is we sum over all the possible values of n. So that's all the possible numbers of eigenvalues that the Laplacian has. And then we are also summing over all possible eigenvalues and all possible components of the eigenvectors. So that's our path integral. And one advantage of this path integral is maybe it looks complicated, maybe not, but in fact you can actually compute it analytically. And so when you calculate it, it looks path integral looks like something like that. It's not very complicated, and because we have an analytical expression for it, from it we can now calculate some observables. And the first thing we can calculate is the effective dimension of spacetime. In order to calculate this, the dimension, we use while scaling. So first of all, because we can calculate the path integral, we can also calculate the scaling of the density of eigenvalues. And then we use this eigenvalue density to plug into the while scaling formula. Now, if you don't know what the while scaling formula is, so the while scaling formula relates the behavior of eigenvalues as they asymptotically go, towards high values. It relates their behavior to the dimensionality of let's say the box that they live in. In this case, it's actually the space-time dimension. But in quantum mechanics, you can imagine having some oddly shaped box, and you can look at the spectrum of the Hamiltonian there. So the spectrum for large wavelengths will depend on the shape of the box, but then as you go to higher and higher wavelengths, the shape of the box starts being irrelevant, and the only thing that matters is the dimension of the box. So here we have the same behavior. Basically, we say for large eigenvalues, the only thing that matters is the space-time dimension, and from that we infer what the effective dimension is. Okay, and the result in the end is that we relate the effective dimension to the number of fermions and bosons in spacetime. So this is the formula 2 plus nf minus mb. It has this curious behavior where it looks like the presence of fermions increases the effective dimension, and the presence of bosons decreases the dimension. So it has, physics-wise, it has similar behavior to a neutron star. And so the previous result, the simple result, where it's just a simple formula 2 plus nf minus mb, that's valid for a trivial spectrum where all the masses are the same. If we introduce a non-trivial spectrum, then we have an energy-dependent effective dimension. So we can have things happening like the effective dimension is higher at lower energies and smaller at higher energies, I think in this example, we just show that it's possible for some choice of number of fermion and boson species and a choice of the spectrum to have at lower energies of four-dimensional spacetime, and then which becomes two-dimensional spacetime at higher energies. And so this is just, we just made a convenient choice to make this happen in the model. It's just, it's reminiscent of various quantum gravity approaches where people argue that the dimension of spacetime reduces to two-dimension when you go to high energies. Okay, so another observable that we can calculate is the expected number of degrees of freedom. So that's the expected size of the Hilbert space defined by the the eigenspace of the Laplacian. So we can calculate that. And additionally, we can calculate the effective volume of the spacetime. The way we do that, well, so we can not only calculate the eigenvalue density that I talked about earlier, we can also calculate the expected spectral gap in let's say analogous way. And so once we calculate the spectral gap, then we can relate it to the effective volume of spacetime because it's related to the gap. It's inversely proportional to the gap. And so we can actually find a nice expression for the volume. And so because we have the expected number of degrees of freedom and expected volume, then this allows us to perform a consistency check. So if you remember at the beginning, I mentioned how from the Hawking and Gilkey formula, which is a classical formula, it's true for a Euclidean manifold. You can just quickly show that the ratio between n and v is a constant plus some higher order corrections, and then that's the classical formula. And then we use this classical formula and put it inside the path integral, and so we made everything quantum. And now after we performed the path integral, we have a new n and v, and we wanted to see is this ratio still behaving the same way? So does it work out well that the quantum result is classical result plus corrections? And it does work out well. So it's some sort of a consistency check where we find that this ratio is still constant plus corrections. So in some way you can think of this also that so inside our path integral, there are contributions which are representable as manifolds, but there are also contributions that are not representable as manifolds. And you could ask yourself, well, what kind of contributions dominate? And this result indicates that manifold-like representations are a big part of the path integral. Okay, I don't know how I'm doing with the timing, but in summary, we performed a path integral using unusual variables of the eigenvalues and the eigenvectors of the Laplacian. We added also free fermions and free bosons to the path integral. Because the path integral was easy to calculate, we could then calculate the effective dimension and volume of emergent spacetime, and we could study how these observables are dependent on gravity and the fermion pressure acting against the boson pull. So we found that there is an energy-dependent spacetime dimension when the mass spectrum is non-trivial, and we found that maybe I didn't comment that when I was showing the plot, but we found that often there is it seems that the good approximation, so the good representation of the correlations that we find is like almost smooth spacetime, which you can show because the effective dimension is an integer. And finally, we show that a consistency check, which demonstrates that the quantum calculation is the classical result plus some correction. So we show that this consistency check is okay. And that's all.
Thank you so much. Let's thank Barbara.